welcome back. This is lecture 11. A few lectures back, we saw that in order to make a good amplifier which can indeed amplify power, we needed a device, or we needed a network that had the following small signal characteristics, right? So if our two-port network were like this, if the two-port network model for the incremental network were like this, where this conductance is Y11, this conductance is Y22, the transconductance in the input side is Y12 times V2, where V2 is the voltage at the output port, and the transconductance at the output side was modeled as Y21 V1, where V1 was the voltage at the input port, right? And if we were to connect an input with a finite source resistance Rs at the input port, and if we were to take the output across another resistance RL across the output port, then we saw that an wish list for our ideal, so wish list for an ideal amplifier would have been Y11 should be 0, Y12 should be 0, Y22 should be 0, and Y21 should be as large as possible, right? Then in our quest for finding such a device, we landed up with one such device, which was a Mosfet, an N Mosfet in particular, which is a 3-terminal device, right? Which is a 3-terminal device. The port 1 is connected between the gate, this is V1. The port 1 is connected between the gate and the source, and the port 2 is connected between the drain and the source. And then we saw that if the MOSFET is in saturation, right? So under saturation condition, that is, what is saturation condition? Saturation condition is, firstly, it has to be on, right? The MOSFET has to be on, which means voltage between the gate and the source has to be greater than some threshold voltage, which is a characteristics of the MOSFET. This threshold voltage VTH will be given to us, right? It is the characteristics of the MOSFET. And under saturation condition, that is, VGS should be greater than VTH. We need to satisfy another condition, that is VD minus VS should be greater than VG minus VS minus threshold voltage, right? In other words, you see that source is common between both sides of this inequality, so they go off, which means that we just have to ensure that the drain voltage is greater than gate voltage minus 1 threshold voltage, right? So essentially, if we can ensure these two conditions, that is VGS is greater than equal to the threshold voltage and the voltage at the drain, or rather this voltage difference between the gate and the drain, the voltage difference between the gate and the drain is not less than a threshold voltage, right? So what is this? What is this inequality telling us? This inequality can also be written in the form of Vg minus Vd, right? Vg, if I move it to the other side, Vg minus Vd should be less than equal to threshold voltage, right? So in other words, what is it saying? It is saying that the gate voltage, the voltage at the gate can be even higher than the drain voltage, but by a maximum of 1 threshold voltage, right? So if these two conditions are satisfied, that is VGS is greater than the threshold voltage and drain is not lower than the gate by more than 1 threshold voltage, right? Then your saturation condition is met, and under the condition of saturation, we get these conditions, that is y11 is equal to 0, y12 is equal to 0, y22, which we also call as the conductance between the drain and the source, that is GDS, is also equal to 0, and y21, which we call as GM, is equal to mu n C ox W over L VGS minus 1 threshold voltage. Now note that this GM, right? What do we want y21 to be? We want y21 to be as high as possible, and this seems to be doable since these factors W over L and VGS minus VTH, or in other words the overdrive, is under the control of a designer, right? So we can pick and choose values of W over L and VGS minus VTH, or the overdrive of the MOSFET. Since we can pick and choose these values, we should be able to get a value of y21 which is sufficiently high, right? So if this is possible, what is the next step? The next step is to see how can we use this MOSFET. How can we use this MOSFET to suit our purposes, right? So in other words, what we are asking is that, okay, it's well and good that does this MOSFET in saturation seems to satisfy the conditions that is required to get amplification of power, right? But I mean, ultimately, you have to put things together. We cannot just simply say, here is your MOSFET, bias it in saturation, and you'll get amplification of power, right? We'll have to ensure that this is indeed achieved, right? So next obvious step is to see how can we achieve both, right? So what is the thing? What are we after? So the next goal is to bias the MOSFET in saturation and apply a small signal input or an incremental input to get amplification. Okay, so let's dive in. So what is the incremental model of our MOSFET? The incremental model of our MOSFET, let's do both together. So what is the incremental of the incremental picture of our MOSFET? The incremental picture of our MOSFET is this. So this is GM times V1. What is the V1? V1 is this voltage. This is V1. But note that this V1 is between a gate and a source. So GM times V1, we can also write it as GM times VGS, right? GM times VGS, right? And where are the inputs and the outputs connected? Incrementally, a source will be connected here, I, RS, and the load will be connected here, right? So incrementally, if this is achieved, what will be, if this is V0, what will be V0 over Vi? So V0 is nothing but the current, that is GM times VGS, right? The current, that is GM times VGS times RL, but the sign will be flipped because of the way the voltage V0 is marked, right? I am drawing current out. I am drawing current out of the resistance RL. So V0 is, that voltage difference across RL is minus GM times VGS. This is the current times RL. What is VGS? What is VGS? How do I know what is VGS? If I do a KVL in this loop, in the input loop, so if I do a KVL in this input loop, what do I get? Is there any current in this input loop? No, there isn't, because I have an open circuited at the input terminal, right? So there is no current. Since there is no current, what do I get? VGS is equal to Vi. So if that is the case, if I plug in this value in the top equation, so V0 becomes minus GM times Vi times RL, and V0 over Vi, that is the small signal gain, becomes minus GM times. Okay, so is this good or is this good news or a bad news? Clearly this is good news, because now this gain, right? So this gain, this AV, is minus GM times RL, right? And can this be made as high as possible? Clearly yes, because RL is fixed, because RL has been given to us by some external specification. But this value of GM, right? This GM is a designer control variable, right? The GM is a designer control variable. We can tweak the GM, right? We can design the GM to suit our purposes by changing the W over L, the aspect ratio of our device, right? Or by changing the overdrive of the device, right? Or changing VGS minus VTH, or by changing the overdrive of the device, right? And note that this VGS minus VTH or the overdrive are the quiescent parameters, right? So that is these are the parameters these are the quiescent voltages at which our MOSFET has been biased. Okay. So now the question is, this still is an incremental model, right? I don't see a MOSFET here. I see the incremental model of the MOSFET. So we have to put a MOSFET in this case, right? So what is the next thing? So what we'll try to see is, what if we replace this incremental model with a MOSFET, right? So let's do that. So how should we replace the incremental model with a MOSFET? Now note that in a MOSFET, the gate is one terminal right? So if this is V1, V1 is the voltage between the gate and the source. This is gate, this becomes the source, right? And V2 is the voltage between the drain and the source, right? So let me just mark it here. So V1 becomes the voltage between the gate and the source, and V2 is the voltage between the drain and the source, right? So how should I connect the MOSFET? The MOSFET is connected like this. Okay, right? So let's redraw this. Okay. Now who decides which is the drain and the source terminal? Because the MOSFET is physically symmetric device. Clearly the voltage, the terminal between drain and source, which is a higher potential, is the drain, right? Because a pinch off happens. I mean, you apply the voltage. When you apply a higher voltage at the drain side, the electrons in the channel get sucked out from the source and get dumped on the drain or drained out from the terminal. That's why it's called a drain. Okay, fine. So now we need to ensure that this is what is the first thing we need to ensure? If we let me do this experiment with you, and if I say that if I directly connect these sources and these loads here, what is going to happen? Right. So let's do this experiment. So let's say I connect the source Vi and the load RL like this. What is going to happen? And for the sake of simplicity, let me just say that this common terminal, the source seems to be a common terminal between the input and the output, right? The source seems to be a common terminal between the input and the output. And we know that every reference circuit, every circuit that we do has one common terminal with respect to which we define all the voltages, right? Because the absolute value of voltage doesn't have any meaning. It's always a voltage difference between the two nodes that we are referring to. And when we say that the voltage at this node is 2 volt or 5 volt or 3 volt, we implicitly assume that there is one reference terminal from which the difference from which is 3 volt or 5 volt or 2 volt or whatever you are measuring, and that reference terminal, that common terminal, we typically call it as ground. So since in this particular configuration, note that it's not true for all configurations, in this particular configurations, since the source seems to be the common terminal between the input and the output, right? So let's call this ground, right? So we call this as a, why is the color not changing? Let me change the color. So we call this ground, right? Since source is the common terminal, we call it ground. So what I would request you to do is to take a moment and tell me what will be the V0 over Vi, or what will be the procedure that we should follow in order to figure out what will be V0 over Vi, right? We'll see you in the next class.